All right, so the first fire that I ever went to produced this vigorously rotating convective column right in front of me. And I was able to use a scanning laser device to look at the vortex structure inside of this. And that was spectacular, but that is not a pyrotornado. And it turns out that vortices of all shapes and sizes are actually quite common on wildfires, some of them quite intense. Here's a sampling of the sorts of things that you can see, but most of these are also not pyrotornadoes. That, however, is a pyrotornado. This occurred in Redding, California in the summer of 2018. And you can see the enormous intensity in here of the combustion at the base and the flaming gases shooting upward through this violently rotating column. It produced winds in excess of 140 miles an hour at the surface, extended to an altitude greater than 15,000 feet. And you can see some of the massive devastation that it did here, including, unfortunately, a number of fatalities. So we're kind of motivated to understand what causes events like this to occur, and we can use many of the same tools that we use to look at ordinary tornadoes and thunderstorms, namely weather radars, to look at the structure of the convective plume, and what you're seeing on the right there is the sense of rotation. So I'm going to walk through some of the ingredients that go into this case. What we're looking at here is some radar data on the top panels. And one of the key features of this is that you need some sort of sense of rotation to begin with. And this comes, in this case, in the sense of wind shear, which is kind of like traffic flowing past other traffic on a highway. But then you need to go from that to collapse that sense of rotation into a coherent vortex, which is what we see in the event. So how does that happen? Well, it happens through something called vertical stretching, or in this case, rapid plume growth. And what we're looking at here is a radar rendering of the evolution of this wildfire plume as it rockets from about 6 kilometers up to 12 kilometers. As that happens, it stretches out a column of the atmosphere, which is very similar to what a figure skater is doing. They conserve their angular momentum and start spinning faster. And it gives us an exponential growth rate, which is what you see on the right there for the sense of rotation. What does that look like on the ground? Well, here is the vortex at its peak intensity. Again, you can see the enormous violence of this event, not only in the sense of rotation, but this huge inflow of wind shooting across the surface. That's what we call sheeting of flames, and you can imagine how dangerous it would be in that scenario. So why does that plume grow so much? Well, it grows due to the release of something we call moist instability. If the plume gets deep enough, it will trigger a convective cloud off its top. And that's what we're seeing here in the satellite image, and we call these PyroCbs. They're quite unique in that you are spanning a huge temperature range from about 1,500 degrees Celsius in the flames up to negative 50 degrees Celsius at the plume top, which is populated by ice. All those phase changes along the way release a lot more heat back into the atmosphere and give us this nonlinear growth. This is what they look like visually, these PyroCbs. This ash-filled column ascends to a great enough depth to condense into this beautiful, I kind of think they're beautiful, white clouds. So what's going on inside of there? We've pointed radars down from aircraft and looked into these things, and that's what we're looking at here. And those brightest red and purple shades are showing updrafts of 130 miles an hour well above the surface. So that's where the stretching is coming from, pulling up on the vortex. So putting all this together, we have a fire in a shear zone that triggers a PyroCb, which collapses the shear into a circulation. And if you're a fan of the movie Twister, that's the same cow. So where do we go from here? Well, we know a fair bit about these things, but we want to know a lot more about what goes into forming them. And we have all the tools, scanning radars and LiDARs. And what I do is I go out to fires and we try to document the evolution of all sorts of plume dynamics. Here's an example from just this November out in Utah. Believe it or not, this is a prescribed fire. It kind of went a little overboard, I think. But it started producing vigorous rotation. This is also not a pyrotornado, but it still produced very strong rotation. These tools can also potentially render real-time warnings for the evolution of a fire. This is the Camp Fire, which devastated Paradise, California. We can track the evolution of the plume, we can track the fire perimeter, and potentially issue real-time warnings. Why is that important? Well, I live in a place where actually I can see things like this in my backyard, but if I'm going to see something like that in my backyard, I really would like a little bit of advance warning that it's coming my way. So that's my story about pyrotornadoes.